It is my great pleasure to introduce Mike Muglia today. Mike is the Assistant Director of Science and Research for the North Carolina Ocean Energy Program and an Assistant Research Professor at East Carolina University. And he's based at the Coastal Studies Institute in the Outer Banks, which is where he is right now. I think you can see some of the Outer Banks in the background, or it's facing land inward, I think. Mike has a bachelor's degree in marine science, biology, and physics, or degrees, an MS degree in physics, and his PhD in marine science from UNC Chapel Hill. And Mike, thanks again very much for doing this, and I look very much forward to your talk. And I'm going to hand it over to Nicole to run the seminar. Thank you.
Hi, everyone. If you guys have any questions during the seminar, please hold them off until the end, unless they're clarifying questions. Then Mike would be happy to help clarify whatever it is that you're unsure of. And I also want to say that next week is our last presentation. So please make sure you look out for that email that'll be coming out next week. All right. Thanks, Mike. Take it away.
Thank you, Martin, for such a kind introduction, and thank you, Nicole, for organizing. And thank all of you for joining me late on a Friday afternoon when I understand, all a bit zoomed and virtualed out. I'm glad that you're here. I'm excited to talk to you. The name of my presentation is The Wild, Wild Western Boundary Current, an observation-based journey to explore the Gulf Stream off Cape Hatteras. Oops. And I like to begin with my acknowledgements, because a lot of the work that I'm going to show is supported by a number of people's hard work, not just mine, and a number of different funding agencies. So my technicians, Trip Taylor and Nick DeSimone, and then my colleagues at UNC Chapel Hill, Harvey Syme, John Bain, and Sarah Haynes, and my friend and colleague, Magdalena Andres at HUI. And a lot of this research was supported by our state-funded Renewable Ocean Energy Program, as Martin mentioned earlier. And it's also been funded by the Southeast Atlantic Regional Ocean Observing Association, which is a regional association as part of the Integrated Ocean Observing System. And then finally, many of the observations were supported by the Processes Driving Exchange at Cape Hatteras project that was funded by NSF. And this was a huge collaborative project off of Cape Hatteras that was multi-institutional, multi-PI, Skidaway Institute of Oceanography, UNC Chapel Hill, NC State University, Woods Hole, and the Coastal Studies Institute all participated. So I'm very thankful that I have all of these wonderful observations in such an interesting area. So what I'd like to present today, I'd like to give a little bit of background on the Gulf Stream off of Cape Hatteras. It really is a really neat place to work. And then just to mention a couple of very high level questions that my research group aims to address, and then present a lot of the ocean observations that we use to address those questions, and then present some of the analysis and discoveries that we have so far from those comprehensive observations. And finally, I know we have lots of engineers in the audience, just touch on a couple of the applications that we're using these observations to develop. This is a sea surface temperature image provided by Rutgers. And you can see here, this is the location of the Coastal Studies Institute. Whoops. I got my red pointer here, yeah. And so behind me is the Croatan Sound, which is what we're looking at here. And as you can see from this image, there are some pretty extreme temperature gradients between the Gulf Stream, this nice hot spot offshore, and the inshore coastal currents. And this is a great place to work because of this giant confluence of all these different currents. You can pick out the Gulf Stream meanders here. You can follow my mouse. And then the colder, less saline Mid Atlantic Bight water, and the more saline South Atlantic Bight water, and what we call the Hatteras Front right here on this image. And so one thing so if we zoom in a little bit on this area, and in this box that I have in the upper left, when I start digging into the observations a bit, this is the area that we're going to focus on. So all the analysis that I present, all the observations that I really really highlight are kind of focused on this area directly offshore of Cape Hatteras. And this is a, a cartoon of what the velocity structure and of the Gulf Stream looks like in that area. So you have this really sheared surface current like this, and then an asymmetric, about 1,000-meter deep baroclinic jet. And then the cool waters on the shelf, especially in the Mid Atlantic Bight. The jet, again, is about 1,000 meters deep. And in our area, it's about 70 kilometers wide, depending on how you identify what you call the Gulf Stream. And I'm showing the isotax here because we're really interested in the speeds and the velocities of the Gulf Stream, especially for our marine hydrokinetic energy work. One thing that's very difficult to do for me, especially in this virtual world, is to convey this sense of how special it is to work offshore of Cape Hatteras on the Gulf Stream. I like to tell people that, you know, we can get in the boat in the backyard here, and within 3 hours, especially in the wintertime, and well, even in the summertime, we've entered a different climate. So being out there, the wave climate is different. Usually the temperature is different. Even in the air, the ocean atmospheric fluxes, which is kind of what I'm highlighting here. This is what we call sea smoke. And this is after a cold front in the wintertime passed over the Gulf Stream when we were working there. And the temperature gradient between the ocean and the atmosphere in this picture is about 20 degrees Celsius. It's just an incredible place to be. Every time I go out there, and I've been working there for about 10 years, there's another crazy experience to see. And I gave a talk to Old Dominion University about this time last year, and one of my colleagues who's published more on the Gulf Stream than I'll probably ever hope to came up to me after the talk and said, you know, it really impressed upon me something that I had not realized. Having done all this research on the Gulf Stream, I've never been there before, which I will never forget when he said that. So it is really a miraculous place to work. And so why is it so miraculous off of Cape Hatteras? Well, Cape Hatteras is what I often call the Mason Dixon Line of oceanography on the east coast of the United States. You have this tremendous confluence of different currents and water masses here. So on the left-hand side, I identify kind of the area in the square here, the Mid Atlantic Bight, the South Atlantic Bight, the MAB and the SAB. You can see a typical Gulf Stream path here, what we call the slope sea gyre, this persistent recirculation. We have a shelf break jet that comes just along the shelf slope here in the Mid Atlantic Bight. And then, of course, we have the deep western boundary current, which happens to pass beneath the Gulf Stream just east of Cape Hatteras. So this makes for some really interesting oceanography and some really interesting physics. If we zoom in on kind of the shelf, you'll see we have this Mid Atlantic Bight shelf water that on average is moving from north to south. This is what we call a Mid Atlantic Bight cold pool because the water is typically much cooler and fresher than the water south of Cape Hatteras. South of Cape Hatteras, we have the South Atlantic Bight shelf water, which is saltier and warmer, and they meet here at the Hatteras Front. And this front gets moved around because of different forcings like atmospheric forcing, and we think the Gulf Stream influences the frontal location as well. So with all this confluence, you have a lot of cross-isobath transport here and a lot of deep ocean shelf exchange, which makes it a really interesting place to work. So the questions that my group likes to address is what role does the Gulf Stream play in influencing this complex current confluence at Cape Hatteras? And for the marine hydrokinetic energy piece, is Cape Hatteras a viable location to extract marine hydrokinetic energy from the Gulf Stream? And to determine that, we use a number of different ocean observations. And here are many of them pictured. So on the left-hand side, it's a picture of my technician and a friend of mine, Stormy, who are doing some work on our research vessel to install a through-hull 300 kilohertz acoustic Doppler current profiler, like this one picture here with the yellow cap. And on top here, we have Robert Todd Todd's spray glider. So this is a glider that he flies, deploys in Miami and flies up to Woods Hole as he's able. And this glider can go down about 1,000 meters, and he makes many different kinds of measurements: salinity, temperature, current velocity, and chlorophyll. And we often recover these for Robert because they don't infrequently get attacked by sharks. And so because the Gulf Stream passes so close to the Outer Banks here, we can get out there and pick them up when they're in trouble. This going overboard here is one of our acoustic Doppler current profiler pods that I'll elaborate on a lot more here shortly. And this is my friend Dana Savage from Skidaway University Institute of Oceanography. Dana is installing a WIRA, a shore-based radar system here in the Outer Banks for part of that NSF Peach project that I mentioned. And then here are a number of observations going out, observing systems going out for that project, a couple of buoys with MET stations on them, bottom-mounted ADCPs near the buoys, and then some more of these pods with lower frequency ADCPs that we deploy in deep water. And we use I'm going to highlight observations from a couple of vessels. We use the RV Neil Armstrong for the Peach project. And so you can see again here, a lot of these pods getting deployed and a subsurface buoy. I'll show measurements from both the Neil Armstrong and from our research vessel, the Miss Caroline. So this is a vessel that we bought not too far from you all in Noank, Connecticut. And we searched the Northeast because there were more vessels than down here. And we settled on this one. What we're trying to do is to build a research vessel to address these questions that can transit our inlets, which are known to be quite hazardous and shallow. So while we'd love to have an 80-foot trawler to equip, we would not get in and out from our backyard with that. So this is the vessel of choice. And so this is kind of my group's opus, having bought this vessel and driven it down here and outfitted the vessel with all kinds of instrumentation. We're very proud of it and we use it quite often. Looking at the back deck of the Miss Caroline, these are a few of the additions that we've made since we got the vessel. We have a through hull 300 kilohertz acoustic Doppler current profiler. In this picture, both of the ADCPs are down in the down position for surveying. So normally when we're running, they stand up and they're kind of extracted, but when we're not, they protrude through the bottom in a stainless steel tube about 3 feet below the vessel. This is a 75 kilohertz ADCP. We have back deck controls to control 2 winches, this one, and there's another one on the boom up here. And then whenever we're running the vessel, we run a flow through thermosalinograph to measure surface temperature and salinity. We also have an A-frame, as you saw in the previous picture, for deploying and recovering our instruments. So as I mentioned, this is the area where we focused a lot of our long-term observations. And I'm gonna talk specifically about 3 different types of observations that we've been making here for about 5 years. I'm gonna talk about the mooring that I'm showing here in the bottom right panel here. Several repeated shipboard acoustic Doppler current profiler transects that have been made across the Gulf Stream here, what we call the Cape Hatteras transect. So that's about 70 kilometers. We use them to study the velocity structure of the stream, and it also helps us identify the variability in the Gulf Stream resource with water depth at this location. And then finally, we've had 3 coastal ocean radars, CODAR 5 megahertz coastal ocean radars installed in the Outer Banks here these 2 have been installed since 2003. So we have a really nice consistent time series of hourly ocean surface current measurements from that network. And what you see in the background here is are the combined are the currents that we measure with the CODAR network. So you can kind of pick out with your eye the edge of the Gulf Stream, and the strength of these measurements, the radar measurements, is that they're consistent, they're made hourly, and we have a nice long time series of them. And you can, with hourly measurements, surface currents, you can start to identify meander time scale structure. So you can see some of the meander crests and troughs here. The time scale for these meanders is about 2 to 10 days. And so you can't really use satellite information because the measurements are not frequent enough or they're inhibited by cloud cover. And so it's really useful for us to look at high frequency variability in the stream. So I'm going to start by talking a little bit more about this pod, the ADCP pod that we've had deployed for about 5 years now, obviously flipping them on about a yearly cycle. And the pod itself contains an 150 kilohertz acoustic Doppler current profiler. It's deployed in about 230 meters of water, and it measures currents over the current velocity over nearly the entire water column. It also has a CTD to measure temperature and salinity at the mooring. And it also has a passive acoustic hydrophone, which my colleague Lindsay Dubs uses to listen for presence and absence of marine mammals. So because we're doing marine hydrokinetic energy research here, that's a very important thing to look for in terms of permitting for the area. So this is something we've been building a really nice archive of acoustic data from. And here's a picture of me getting ready to deploy one of these pods. This is what they look like. This is kind of a special deployment for us. This is just an acoustic release here. The ADCP sits underneath the pod here. And we outfitted this one with some deep water lights and actually a GoPro with a deep water housing on it. And we wanted to video the deployment itself and get a look at where we're actually dropping these things. And so I'm hoping that I don't have OSHA officers out in the audience, because this deployment was done quite a long time ago. We've certainly stepped up our game since then, but I'll show you what it looks like. This was a stellar day for a deployment. It was calm, as you can see. We're on the edge of the Gulf Stream there, straight off of Hatteras, putting this thing overboard. And this is the 150 kilohertz ADCP. These guys here are the acoustic releases. And we're going down under the water here. And this was kind of the backyard way of filming. We're actually zip tying the cable for the camera device as we go. I'm watching it on a monitor and fretting that the release is going to slam into the ADCP heads. And then we can actually see it on the ship sounder as it goes down. And this was actually our first visual glance at what the bottom looks like where we drop these things. So the interesting thing here, there it goes, it just got dropped. And then we lowered the camera a little bit more to get a better look. And if you look really carefully, you'll be able to see some tiny little anemones on the bottom, like here. And the funny thing that's not in this video is that we lost the mooring base for a different type of mooring we were using. And as we drift away and we're getting a good close look at the bottom here, we saw some of the line from our lost base. So in the vast ocean, it was kind of a surprise. It was exciting, but funny. Let's see here. I have a little trouble getting from this to the next. There we go. So I'd like to highlight the discoveries that we've made with several of these observations. So from an MHK standpoint, we're really interested in what the currents are at this one location. And the reason for that is that this location it's relatively close to land. It's in relatively shallow water, about 230 meters. And especially that it might be one of the only viable places outside of the Florida Straits where one could get access to the Gulf Stream consistently to get marine hydrokinetic energy. And that's because the Gulf Stream variability and position here is least after the Gulf Stream leaves the Florida Straits. So from about 3 3/4 year time series of observations from that ADCP pod, we're able to look at what the current speeds are, both 40 and 76 meters below the surface. And as you can see, I'll kind of highlight it in yellow here, about 64% of the time, we have currents here that exceed one 1 meter per second. The reason that I have 76 meters is we had a previous publication where we were kind of focused on the 76 meters below the surface, and I was curious, what's the big difference, and when you're really thinking about how close to the surface do you really want to get, and what you get for getting closer to the surface with a theoretical turbine, what's the comparison? So you get about 10% more exceedance of 1 meter per second if you get a little bit closer to the surface. And of course, we also have some currents that exceed 2.5 meters per second at times. So this is really valuable if you're thinking about cut-in speeds, or if you're thinking about what your actual energy extraction will be from some kind of device here. Another interesting thing that really popped out at us from 3 years of CTD observations on the bottom there at the pod, if you look at these TS diagrams, we have temperature on the y-axis, salinity on the x-axis, and the isopycnals are identified here. What oceanographers love to do, and I'm sure we have some in the audience, is to classify different water masses by temperature and salinity, and then argue about them ad infinitum. But what I've done here is shown some of those different water mass classifications: the Mid Atlantic Bight, winter and summer water, the South Atlantic Bight, the deep slope water, Gulf Stream water, and not discernible deep slope and kind of offshore North Atlantic water. And what jumps out at me from looking at these observations is that you have these kind of divvied this up quarterly, and there's this bimodal behavior here where we have a very different winter and spring and summer and fall. So this is like the colder water and the warmer water, and we're really exploring some of these shelf deep ocean export events that we've seen in some of these observations. And this is like when the Mid-Atlantic Bight water is cold enough to slide down the shelf slope beneath the Gulf Stream. So this is something that's kind of an ongoing project of ours. It's mentioned in a manuscript that'll be out soon, but I think this is a paper unto itself when we kind of dive in a little bit deeper. All right, let's take a look at some of the vessel observations along this Cape Hatteras transect and what they tell us. So again, the vessel transect starts at about the 100-meter isobath and goes about 70 kilometers offshore, and we've used both the Miss Caroline and the Armstrong to do this transect several times, probably approaching 20 times. And we're able to see the Gulf Stream velocity structure, as I'll show you, and the variability in that velocity with water depth, which is important for MHK considerations. So this is a typical day on the Miss Caroline when we're running the ADCPs. We're leaving from the backyard here at CSI, and we transit out Oregon Inlet. This is in the wintertime, so you can see the cooler cold pool water. And then here at about the 100-meter isobath, we're starting to see Gulf Stream water. And so this is the water temperature from the thermosalinograph, and these are the current speeds that are measured from the 300 kilohertz ADCP and the 75 kilohertz ADCP. And you can kind of see this velocity structure of the Gulf Stream that we'd expect here. If you look really closely, you can kind of tease out the line that delineates the measurements that are made with the 300 that are higher resolution from those made with the 75 kilohertz. And what's really, really interesting is this extreme gradient that we see here. And so what this means for us when we cross that gradient, which at times is about the length of a football field, is we might go from a wonderful ride to hell on earth, or we might go from a rather bumpy ride in the summertime when the wind's out of the southwest to a nice, smooth, beautiful day when we get on the Gulf Stream and the wind's blowing with the stream. And it really is like stepping into another world as soon as you cross that. And it's amazing how strong that gradient actually is. If we take a look at some of these observations that we made with the Armstrong has 3 ADCPs. It has a 300 kilohertz, 150 kilohertz, and a 38 kilohertz ADCP. And so what I've done here is I've shown the bottom in this picture. This is depth and cross shelf distance along that Cape Hatteras transect, about 70 kilometers. And we've divided up the current into its long stream V and cross stream U components. And then this is the current speed. And you can see, as I mentioned, the Gulf Stream is about 1,000 meters deep here off of Hatteras. And the thing that's really interesting here, and this was a new discovery that we made after a science verification cruise on the Armstrong. You can see we've kind of highlighted this color. You can see in the cross stream, this is the upper limb of the deep western boundary current. So this is upper Labrador seawater. And this water is flowing in the opposite direction from the Gulf Stream. This water was previously thought to be advected at Cape Hatteras to the northeast, so not to persist beneath the Gulf Stream. Kind of at that crossing point, it was thought that this water was advected off to the northeast and kind of sheared off. And we found through several cruises that there is this continuous flow of upper Labrador seawater south of Cape Hatteras. So that was cool. If we could dig in a little bit more to some of the observations that we made from the Armstrong, see some really interesting physics that's important if we're considering how we might put an MHK device in. So on the left hand, we have the downstream velocity. And you can see, again, this upper Labrador seawater. And this black vertical line here is where we made a CTD cast to about 1,600 meters, which is how deep the water is at this location. And what I've shown here are the shear in the downstream and cross stream velocity. This is the shear and downstream velocity with depth, and shear in the, gosh, I can't even see here with all this stuff. Let me see. And this is the shear in the downstream velocity with cross shelf distance. And a couple of things that really pop out is that we have these really strong shears in both in what we call the cyclonic shear zone. This is an area of relatively high relative vorticity in the Gulf Stream on the landward side. And then you see that we also have this really high shear area where we have this change in water masses from Gulf Stream water to upper Labrador seawater. So we'd like to investigate that a little bit further. So I'm kind of highlighting the CTD cast, and what we looked at were the downstream and cross stream velocity components with depth at that CTD cast. And so we have the downstream component V, the cross stream component U, and the measurements made from the 3 different ADCPs, which have different resolutions. So the 300 kilohertz ADCP has 2-meter resolution, and that's the green here, doesn't go too deep. And then the 150 kilohertz ADCP has 5-meter resolution, and the 38 has 20-meter resolution. And what you notice that's interesting here is possibly some evidence of internal waves, and we can't tell whether they persist below the measurements of the 150 kilohertz ADCP. The 38 kilohertz ADCP can't resolve them, so that's something that we're really interested in looking a little bit more detail. It's a tricky thing to measure. What does that do to the shear squared? So you can see that we have tremendous shear squared in the kind of the Gulf Stream jet area near the surface. And then you can also see right here where we have the intersection of this red line between water masses at about 500 meters, we have enormous shear squared there as well, as you might expect from current flowing in opposite directions. So what we did is we looked at, from the CTD cast, we looked at the buoyancy frequency squared along that cast. And so the buoyancy frequency gives us a parameterization of how stratified the water column is. So we can see there's quite a bit of stratification up near the up near the jet of the stream here. And then we see a good bit again, as you might expect, right where we cross over there from the Gulf Stream water to the upper Labrador seawater. And so we used both the buoyancy frequency squared and the shear squared to look at the Richardson number, which is a parameterization that tells us whether the shear is significant enough to mix that stratification out. And kind of the rule of thumb for the Richardson number is if it falls down to a quarter, that's significant enough to mix that stratification. There is some literature done that's published that suggests that maybe in the North Atlantic, 1 is low enough for that mixing to occur. But it's really interesting to kind of take a look at this area right here, again at the crossover, and see that we do get low enough Richardson numbers to see some of that mixing. So this is an interesting question for a number of reasons. This might be an area where there can be deep water and shelf exchange where water is mixed into the Gulf Stream and then upwelled. And the other thing that's interesting here is you can see that we may even get, if we were able to resolve some of those internal waves and they persisted at this depth, presumably the shear would be even higher and the Richardson number would be even lower in this area. So we thought that this was a pretty interesting result. So the other thing, last but not least in the observations I want to talk about are some of the features of the Gulf Stream that we've looked at with our HF radar network. And so again, these provide consistent long-term surface current measurements hourly. What I'm showing here is what we call the total surface currents from the entire array. And they measure surface currents being the top 2 to 3 meters of the water column. But what we did is we took a look at what we call radial currents from the individual radars. And the reason for this is because there are some challenges with quality control and with getting uncertainties with the radars. And it's easier to start at a simple level and kind of take a look at each individual radar radial surface current. And so what we did is we focused that effort on the radar that we call Hattie, which is located here in Buxton, North Carolina. And this is a typical hourly radial surface current measurement that we make from Hattie. And what you'll notice is you can see these hot colors. This is where the Gulf Stream enters the radar footprint and exits the radar footprint. And you notice, well, what's going on in here? There's no Gulf Stream here. Of course there is, there's continuity here. The way the radar works is it uses the Doppler shift in the electromagnetic wave that's emitted. And so when the Gulf Stream is perpendicular to the radar, we're not able to measure it in this kind of throat that we have here. So what we did was we are trying to design a method to look at Gulf Stream variability with just the radar, with just the radials. So we look at a time series. In this case, we're looking at a month of hourly radials. And we chose to select the mode mean maximum radial velocity bearing from 1 month of hourly radial measurements. And so that's kind of a mouthful. All it means is that I step through all these hourly measurements and I look at the bearing that has the highest velocity most of the time. And I choose that for analysis. And then we select the location of the largest radial velocity gradient along that bearing. And we use this as a metric for the edge of the Gulf Stream. We look at the location of the largest radial velocity. We use this as a metric for the Gulf Stream jet. We came in 15 degrees from doing this in the southern area and in the northern area so that we have some more information, but we wouldn't be doing analysis in this throat area again. And we made the same estimates with those bearings. And then we did it with another radar. And so what you start to see, these are the monthly averages. This is the location of the Gulf Stream edge based on that algorithm. And this is the location of the jet. And we're able to start to kind of connect these proximal bearings and get some idea of what the orientation of the stream is. And then we look at the distance between the edge estimate and the jet estimate, and we use this as a metric for what we call the cyclonic shear zone width of the stream. And so you could build a time series. This is done for that month that we were developing the analysis on. The reason we chose November 2014 is because that's when we had some really good quality information from this radar Hattie. And you can see that on the y-axis here, this is the distance from the radar along the 72-degree bearing to what we call the edge and the jet. And you can start to see the variability that you expect to see from Gulf Stream meanders that propagate past that bearing. And this is a very powerful way of looking at the Gulf Stream and getting high frequency estimates of the variability consistently that are not available from other instruments. So we've published on a number of these discoveries. The analysis that we did with the CTD cast and the velocity measurements from the Armstrong was just accepted for publication in the Marine Technology Society Journal. We did another more general publication on marine hydrokinetic energy from western boundary currents. And we also published on the continuous flow of upper Labrador seawater around Cape Hatteras. So I know we have a number of engineers in the audience. How are we applying this to marine hydrokinetic energy? We have a couple of projects that are funded by multiple funding sources. Our State Renewable Ocean Energy Program, the Defense Advanced Research Projects Agency, and the Department of Energy's Water Power Technologies Office. With my colleagues, these guys are the leads. Actually, I'm just a lowly oceanographer on the team, but Chris Vermillion, Matt Bryant, Ken Granlund, and Andre Mazzolini have been developing both a tethered coaxial turbine. So this thing is yawed so that the counter-rotating turbines obviously cancel out the torque, and the yawing allows fresh flow on the surface turbine in some areas that are not, it's not inhibited by the deeper turbine. And so this is kind of at a prototype stage. We hope to deploy this in the near shore shortly. It's relatively easy to deploy. It fits in the palm of your hand kind of thing. And then we've also been working on an ocean kite system for various applications. One of them is to get energy from the Gulf Stream, and others are from tidal resources. This is in almost the test stage. We'll be tow testing this kite in fall of next year. The way this one works is it uses a generator that's on the winch system, and it spools out under high tension and spools out under low tension. We've also explored using this concept as a ducted turbine and tidal flows, but currently we're working on the kite version of it like this. And so these are exciting projects, and we're looking forward to testing them soon. And that's pretty much it. This is a picture of Miss Caroline and us out working with NOAA about a month or two ago, and you can see the deep blue of the Gulf Stream. And again, it's difficult to impress upon you how miraculous it is to be working out there, but hopefully this conveys a bit of that. And I'm happy to take discussion or questions from anyone in the audience.
Thanks so much, Mike. That was a really excellent presentation. And I think we all could get a good idea that the Gulf Stream is a pretty unique place to work. So if anyone has any questions, feel free to unmute yourself, or if you want, you can type it in the chat and then I can read it aloud for you. In the chat, we have someone saying, amazing presentation. Thank you.
Oh, thank you.
Hey, Mike, it's Chris Seaton from former days of the RV Neil Armstrong.
Magdalena said I might run into you. I didn't even know you were there. It's nice to hear from you.
Yeah, man. Cool stuff. I was wondering, in the specific engineering application processes, have you guys teamed up with anybody, or is it really just NC State that's looking at, like, does anybody see this as economically or fiscally viable? And have you started conversations with people like that?
That's a great question. So we have recently teamed up with private industry folks to do the winch system. We've tried to team up with Martin on something that just wasn't funded for ARPA-E. So the answer, the short answer is yes, we have, and there are other folks involved in this in addition to the main folks leading the charge at NC State. In terms of viability, yeah, we do think we can get what's called the levelized cost of energy very low for the kite system. And the reason is that the kite system doesn't quite have all the heavy hardware that you have if you were to, say, put a turbine in the water. And so, yes.
We have another question from Pat O'Byrne. He said, great talk. How long do the ADCP transects take to complete? And what is your cruising speed?
That's a good question. So we usually cruise at 10 knots or less. 6 or 7 is typical. They take, I don't know, about, sometimes we'll do just one leg and sometimes we'll do them out and back. So it's probably between 4 and 6 hours to complete. So for us on the Miss Caroline, because we don't like to come through Oregon Inlet at dark, it's a 2-day trip. We'll maybe go out late morning and come back the next day.
Thank you. Any other questions?
Yeah, Mike, really nice talk. Just a quick observation from a mechanical engineering perspective. When I hear TS diagram, I think about temperature and entropy in some thermal cycle.
Yes.
And it's kind of nice to, I mean, you know, translation between the disciplines is often an interesting thing. So, but those were very interesting plots. From an energy perspective, ocean current energy has one major benefit over, say, tidal or wave energy, in that you can really get base load power from it if you manage to stay in the current the whole time, and if the current is strong enough. So with the current meandering, is it still feasible to deploy a system that will remain in the current all the time? What is the lateral extent of the current meandering, and you know, are there mooring systems that can compensate for that? All those things.
Yeah, that's a great question. So we got a little bit of seed funding from our state program to investigate that, right? So instead of having some tethered turbine system that's fixed, would there be some way of designing a glider or an AUV to kind of follow the current? And we've gotten a fairly long way with that, and that the DARPA project that we're on is actually a glider that uses a kite to recharge. So in that instance, you theoretically, you could move with the stream to some extent, right? So what I mean by that is the tether length can get to be a problem in the deep ocean. So while you might want to follow the stream 30 kilometers offshore, you'd be in 4,000 meters of water, and you need to moor the glider to be able to pay out the kite and get electricity. So there's some of that capability, yes. So the variability in the envelope of the stream, and again, it depends off of Cape Hatteras. It's very different everywhere. So there is variability in position in the Florida Straits as well. It's less. There's much greater variability off southern North Carolina. And that has to do with the oceanography and the physics of the steepening shelf slope and the vorticity constraint that's kind of introduced off of Cape Hatteras on the variability in the stream there, which is kind of why we're focused there. So I guess if you want to ask, like, how much does the stream vary off of Cape Hatteras, it's about 10 kilometers in the literature.
Okay, thanks.
I think Will had a question.
Hey, that was a great talk, and I appreciated the picture of the wave in the background of the radar image where you had the high frequency radar set up. So I'm really interested in kind of exchange across the Hatteras Front, and I was wondering, you've done a lot of kind of open ocean measurements of the Gulf Stream, but I was wondering how the Gulf Stream and like the seasonality of different water masses moving around affected transport across that. I mean, I know that's a big question, but
that's a good question. And so let's see. Well, thank you for the accolades on the presentation. And yes, it always comes out eventually. I'm a surf junkie, and Hattie is located at the lighthouse in Cape Hatteras, which is kind of surf mecca for the East Coast, which is why I chose that picture. And the Peach Project focuses much more on that complex confluence in the Hatteras Front and the exchanges and all these different pieces. And so that's certainly something we're trying to get a handle The mixing along the front there, there's a pressure gradient that's caused by that front, which drives, well, there's kind of the confluence that drives cross-shelf transport, but also that pressure gradient, right? So the front itself can be extremely distinct. And of course, you have to think about it in terms of 3 dimensions. You can see it like a tide line when it's calm. In the literature, it's kind of discussed as being about 10 kilometers wide, but it varies a lot depending on the mixing, right? So if there's a very energetic environment, things get mixed much more. But it's very pronounced. So I hope that answers your question. So the Gulf Stream is it's about a meter high slope of water. So when you wiggle that back and forth, you're driving this big pressure gradient offshore that certainly kind of influences all that exchange from the shelf and even the frontal structure of the Hatteras Front. So we've got a lot of work going on that shows how some of that Mid Atlantic Bight water comes down the front and slides down the slope underneath the stream, and you have these crazy processes going on there. That's part of the Peach project and the analysis. I hope that answers your question.
Yeah, I think I worded it not as well as I had hoped, but yeah, I was like, is it particularly for surface waters, is it a fairly permeable front? Like, do waters move back and forth across that? Is there, for instance, if you had larvae, would they be exchanged across that front?
Dana Savage is the best person to ask about that, but we kind of think about it as a highway for the larvae to move along the front rather than across it. So it is a bit of a density barrier for that, right? Mm-hmm. And that varies a lot depending on the kind of mixing and 3-dimensional structure that you have. But we think about it moving off. We think that it may be a pathway for larvae to move offshore and onshore.
Okay.
As opposed to back across. And so in terms of, well, this is another kind of soapbox thing to say, but in terms of the biology, the chemistry, the physics, it's the Mason Dixon line for all of that, right? So that's really cool. And some things that we've seen is that, off of Nag's Head, north of Cape Hatteras, we've caught Maine lobsters. And just south of Cape Hatteras, you can catch Florida lobsters. I mean, that's kind of how it's an example.
All right, awesome. Yeah, thank you.
You're welcome.
All right, does anyone else have any questions they'd like to ask? Okay, so if not, thank you again, Mike. That was an amazing presentation. And I just want to remind everyone that next week is our last presentation that we'll have for the fall semester. So I hope you all can join, and have a great weekend, everyone. Thank you.
Thanks for your time.
Thanks again, Mike.
Afternoon.